Example 2. A bone found in a state park in Utah contains 12 grams of carbon-14. The half-life of carbon-14 is 5,700 years. So we're going to use our equation here, and we're first going to solve for K. Now, just so you know, carbon-14 is a radioactive substance that will just kind of decompose. And so there's a certain ratio between carbon-12 and carbon-14 that is always maintained. But once an organism dies, therefore carbon-14 isn't being made anymore, so it's just going to be decomposing. And so we can measure how long ago that was, or how old the bone is, based upon the carbon-14. So this is really important. So this is also known as carbon dating. So let's first solve for the K value. So we have our equation. So what do we know? So we have 12 grams, and then we have the half-life of carbon-14, which is 5,700 years. So let's go ahead and use the 12 grams. And we're going to actually use that as our starting amount. So we have 12 grams. And then let's just take the half-life of that. So how long until that becomes 6? So we're going to go from 12 to 6. So that will be on our left-hand side. We're going to still have our E, right? And then we have K, which is what we're solving for. And then we have T, which is 5,700. And that would be 4K. So this is part A. Now what do? We just go ahead and divide by 12 on both sides. So we get 1/2 on the left-hand side. And then we're just left with E to the 5,700 times K. So let's take the natural log of 1/2, because this gets reduced to 1/2. Now we take the natural log of E to raised to the 5,700 K. Now what does this become? Well, this gets kicked out here, so we get the natural log of 1/2. 5,700 K times the natural log of E. This just becomes 1, which is really nice. And then we just go ahead and divide on both sides. This is 5,700 to get K by itself on the right-hand side. So let's get our calculators out. I'm going to use this one. So we take the natural log of 1/2, or we can just go 0.5. Then we go ahead and divide it by the half-life time, which is 5,700. And what do we get? Well, we get a really small number, right? This is negative 1.2160 times 10 to the negative 4. So all that means is we're just going to move that decimal over to the left 4 times. So let's look at. So we get K, which is equal to this. Let's just add a lot of zeros right here. And then we get 1, and then the decimal 2160 times 10 to the negative 4th. Well, in order to get rid of this 10 to the negative 4th, what we're going to do is we're going to move this decimal over 4 times to the left. So we go 1, 2, 3, 4. So we have 0.0001216, and that's our K value. Now let's go ahead and solve for part B. So how old is the bone if it was initially 32 grams of carbon-14? Well, that means now this 12 is going to be our ending amount. Our starting amount is 32 grams. And then we have E raised to the, so we have, this is negative 2, by the way. So this is negative 0.0001216 T. So we're solving for the time. So let's go through this. We go ahead and divide on both sides. Then we're going to take the natural log of both sides. What does that become? Well, the natural log, 12 over 32 stays the same, but we get this number kicks out times the natural log of e. This becomes 1. Then we're going to go ahead and divide on both sides this our k value. And then we can solve for time this way. So let's get our calculators out. So we go to our function, we take the natural log, go to the numbers, 12 divided by 32, close that, and then we're going to go ahead and divide by our k value, which is our negative 0, 0, 0, 1, 2, 1, 6, 1, 2, 1, 6. Look how nice that is when you need to fix your mistakes here. And then what do we get? We get 8,066. So we'll just round to the nearest whole number, and that's for years. So that's how old the bun would be if it originally had 32 grams.